Hello and welcome to KAUST Live. We're coming to you from the Enrichment in the Spring program. This year's theme is City of the Future, and here to talk to us about that is MIT professor Kamal Youcef-Toumi. Professor, thank you for joining us.
Well, thank you for having me.
Yeah.
Thank you.
So, as I said, we're talking about City of the Future, and some of your research is very relevant to this, including some smart grid research. So get us started in talking a little bit about smart grid research and where that is right now.
So, so the grids, as you know, are used, to provide electricity, to different users like commercial, industrial, and residential. And then the traditional one is that the electricity is generated by, let's say, either gas or some other fossil fuel, sometimes nuclear, right? So our interest has been in looking at how the generation is happening, right? And then we combine with the renewables, could be from wind or solar, and then looking into how the electricity is transmitted and then distributed, to the users. So this is like one layer that has, you can call it maybe the physical layer. And then on top of it, there would be the controls layer, so that it monitors, in the end, in a sense, like balancing between the electricity that is being generated and used after it, right? And then the third layer is the market, that does all the prediction and the costs and so on. So when you have a smart grid, right, so then everything is automatic and well balanced. And even when there are surges, because of demand or some other sources, that it can, rebalance, very quickly. The other thing that you can do is with what is called like microgrids, so that you can have like a smaller grids that are connected together. And that is not only for efficiency, but also for resilience and robustness, so that if something goes wrong somewhere, you can immediately identify it and you can localize it, and then the rest of the country or the region will operate as if nothing has happened. The other important thing about the smart grids is that the grids are connected with each other, from country to country. And so if the grids are smart, so that when there are imbalances, that happen, that they can automatically adjust in that way. So this is maybe from the operations and concepts point of view. In the work that we've done, so you can look also into the models, for example, the simulations, the control systems. Also maybe ways of sizing. So for example, if you had to add, let's say, a new type of generation, for example, adding wind or solar, or maybe storage, right? So depending on the location, depending on the capacities, how all those are being affected in that way. And you look at them like in a systematic and generic point of view. Yeah.
Right. Are there examples where this is happening already, or in some sort of lesser form to what we'll see in the future?
Well, it is interesting is that even, in many countries, some of them are very well developed, and they are still maybe using like a telephone, and then they call and they need, for example, 20 megawatts or something like in the next 15 minutes or the next half hour. Yeah, but you would want them to be, more smarter than this. The other thing is there are countries where solar is being generated, right, for example, as a renewable energy, but the grid is not ready to take that energy. So it's as if you have the energy collected, but then you can't use it.
Right.
So yeah, so these are some of the, I think, issues like that.
Maybe a really captivating thing, because you talked about connecting countries.
Yeah.
A country like Saudi Arabia that could generate a tremendous amount through things like solar.
Right.
Could they foreseeably in the future transfer that to other countries, be an exporter in that way?
Yes, yes. I think any country that has maybe technologies like this, you know, that they can not only receive, you know, the electricity maybe from other countries, but they can also distribute it to nearby countries in that way. Yeah.
So part of your work is on dynamic systems and controls, and you were getting into that a little bit. So go a little bit deeper. How does that relate to the...
So when we say dynamics and controls, these are, for example, the grids, you know, robots, cars. We've done work with Toyota before, with Denso company, you know, years back. For all of these automated systems, whether they are small scale or large scale, you know, we need to model them, so the models can be based on physics from first principles. The models can be from input-output data that we collect and then make models out of those, or it can be a combination of the two, and then those models we use to design controllers, and these controls will run in real time, so that the machine or the process or the systems that we are controlling, that they will do what we want them to do.
I see.
Yeah, so that's basically what we call it, dynamics and control. Of course, it involves not only the modeling, the design of these systems, the instrumentation that goes with it, a lot of sensors, the interfaces, how to connect machines, you know, to computers, whether the computers are on board or somewhere else, and then in the end to run them in real time. Yeah. Yeah.
People talk a lot about the Internet of Things, so that sounds to me like the sensor component to that.
Yeah.
To what degree is that part of your research?
So the Internet of Things, in fact, and some people call it the industrial intranet. There is a big consortium that General Electric leads that consortium with other companies like IBM and Cisco and so on. And basically what you're looking at is instrumenting things. I mean, today a lot of things are already instrumented. Your phone, for example, cars, and imagine you can instrument them even more, so that you collect the information, and then that information is either processed in real time and right on those devices, or they are maybe moved somewhere else and they are processed. Information can be shared, and so this Internet of Things, or the industrial Internet, is maybe more than just adding sensors to things, you know, because you want to add maybe more intelligence into these things. For example, you can look at maybe aircraft engines, you know, that are instrumented, and you can imagine the engine reports perhaps to the, you know, to the company about its health. You know, the temperature is fine, the pressure is okay. You know, and then maybe even maybe predicts, you know, into the future to say, you know, maybe today I'm okay, but tomorrow at 2 p.m., you know, this part is not feeling well. So these are, I think, very important technologies that you can combine, you know, not only with the instrumentation, and then any other technologies that you can not only monitor these systems as they are behaving, but perhaps to even look at them into the near future, because that is all associated with like safety, for robustness, for comfort, for many other reasons you want to do that. I mean, you don't want like your car to, you know, all of a sudden shows up like the red lights, right? And then it says, you know, now you need to stop. What if your car, let's say, alerts you ahead of time, right? It say, hey, Nick, I'm okay today, but tomorrow or next week, maybe the battery is not going to be okay.
Right.
So then you have time to plan and do all of that, yeah.
Right.
Yes.
And then hopefully the smart car actually takes it to get the oil changed or the
Yeah,
battery
yeah,
changed.
right. Yes, maybe it goes by itself, right?
That's right.
Yeah.
Do we, as we deploy these millions of sensors
Yeah.
and these networks, do we have the computing power to be able to handle this amount of data? Is that lagging behind, or?
Well, I think depending on what kind of data you're collecting and what kind of processing you're doing, right? So if one is I don't know, taking a signal that is let's say representing temperature, in some process or in some system, or let's say in your car, maybe I don't know, some then I mean that one maybe doesn't have much data with it unless one is collecting it for a long period of time. But then if you go to images, right, and then depending on the rate at which the images are taken and also the resolution in the images. So if it's an image, let's say it's 1024 lines by 1024 pixels per line, then it's like about 1 million pixels, right? And if you are doing, maybe video rate, 30, maybe 25, 30 frames per second. So then that capacity of the data, adds up, very, very quickly. Yeah. So this is just from the data point of view, and then you need to process it. So the question is whether these things are being processed in real time, and then the answer, is needed at that time, or that it could be processed either in real time or offline, but to be used later. So in that case, maybe one can have maybe more time, and those are the requirements on the computing power. I mean, computing has been increasing and decreasing in cost, but also the capability have been increasing tremendously.
Right.
So, but then depending on the application that can require things that are much different in that way. Yeah.
It sounds like when you talk about that what you're saying is that we need systems that will decide between stuff I've got to do right now and then stuff I can bank for learning, essentially. Is that generally the way that it works?
So depending on the applications, right? So there are, and also the data that is needed. Sometimes, as I said, data that you need then, and you process it because maybe you're using it for the real-time control. And then there may be that same data, or maybe combined with some other data that is used, let's say, for decision-making, or maybe for planning. So those sometimes, can be done at a slower rate, right? So maybe you have one loop that is running very, very fast, right? And then you have another outer loop that is running slow, maybe that is looking into the environment and checking things, right? And may not be running at that high rate in that way, So.
Your work, and I'm fascinated by this, your work is at one point at a very macro level and looking at different systems, and then some of your work is working at below the nano level in video. So talk a little bit about atomic force microscopy.
Yeah, okay. So the work on the nanoscale, we started, way back in the maybe beginning of the 90s or so. But the very exciting thing that we've been doing recently is building these scanners, right? So that you could use to scan things, and we can talk about the things in a minute. That you can not only just take images, but you can take videos, at high speed and high resolution. And so then you can see things live in front of you, right? So for example, let's say you have a material like calcite, right? And then you want to see how this material dissolves when you put acid on top of it, right? So then we put acid, or we start scanning to look at the material. You put acid after that, and then you can see how the material, is dissolving. It turns out, in this case, that it does not dissolve like you put, for example, a cube of sugar, in your coffee, and then it dissolves, completely. It turns out here that the dissolution process starts at some pits that are about 1 nanometer in diameter, and then quickly it transitions into a dissolution that is layer by layer. So you can see layers being retracted, and it's kind of removed, right? It's like a cake or like an onion that you're removing, like one layer after the other. You will see that those layers are actually being retracted along the crystal lines of the material. You can also see the rate at which it's dissolving. So all of this information that it will be very difficult, I think, to get it like from maybe still images, right? But now you can see how it is happening. Or for example, if you are putting like materials, doing deposition, for example, some material on top of the other one. And then you can look at it in that way. So maybe another application could be like in maybe a medical field, for example, where you can see maybe a cell or a microbe, how it responds, to an antibody, for example, and then you can see maybe in real life, how it is responding to this thing. Yeah. So here, the thing is, as I said, if you are taking images, high-resolution images, and then we need to do it at video rate, maybe 25 or 30 frames per second. So today we are handling about 20 million samples per second. Right? And then we are in the process of building another prototype and a new generation instrument, so that can handle maybe a lot more than that. But this data that you transfer from the instrument to the computer, about 20 million samples per second, and then you process them in real time. Some information is used for the real-time control. And the other information is for visualization, so that the user can see what the instrument is doing. And here, for the real-time control, is not only to control the scanner as it's moving around, and then perhaps, because this is like at the sub-nanometer scale, so anything that happens around can disturb it. So maybe you can breathe on it and it can expand, right? Maybe about that small amount that can affect maybe your measurements, or somebody maybe walks, in a hallway, or maybe a truck goes down the street, right? So all that vibration can be transmitted. So of course we have vibration isolation. We have things that try to minimize all those effects, but you still have to do other things to be on the safe side.
Well, this is a perfect segue. So I wanted to ask you about robotics and automation, and I wonder at what point are we going to set up labs that have robots and automation, and they're off doing research, and we're just getting results?
Yeah, actually, the thing is that it's happening now in the sense that that it's not that we don't want to do those jobs. Right, that the people do not match, with their skills and talent and so on, do not match that. I'll give you an example. So if you look at the countries, for example, in Southeast Asia, you start maybe from South Korea to China, Japan, and you go down to Taiwan, and then all the way to Thailand. So maybe 25, 30 years ago, they had people that maybe with high school education or maybe some other type of training, and they are able to work in the factories and do, these jobs of assembly and whatever you need to do there. But today, when you look at all of these countries, all of the young people are very, very well educated. They have bachelor's degrees, master's degrees, PhDs. And so the pool of people that work in the factories is smaller. So you even have to import people, right? Or do something else. Something else, maybe, you know, machines that can do things. So we have one of the projects that we are doing in robotics is where, you know, maybe the robot watches me do something, and then it learns from me, and then it can teach the other robots, right? And they talk to each other. Oh, we don't need Kamal anymore, you know. So, okay. So yeah, and then they learn depending on you know the situation. So and as you know today, you know this whole topic of learning, you know, is very very hot. And needed, I think, in many of these applications. Yeah.
I'm going to switch tracks on you a little bit.
Sure.
Your engagement with research institutions in the kingdom is quite long. Talk a little bit about how that got started and the different you know, institutions that you've worked with. Yeah.
Sure. Yeah. So of course, you know, I come to Saudi Arabia maybe 2 or 3 times or maybe more a year. So we started, you know, great collaboration with KFUPM, King Fahd University, for petroleum and mineral, and that was about a 9-year collaboration. A lot of it was on clean water, clean energy. We had also some other activities in design. Specific program that was added to that collaboration right from the beginning on the Saudi women. So this is the Ibn Khaldun program or fellowship program for Saudi women. So this is a very, let's say, elite type of program. Aramco company also, with thanks to you know, His Excellency Khalid Al-Falih, you know, who you know gave the boost, you know, to the program, and Dr. Khalid Sultan, who is director of KFUPM, you know, he was the one that looked at all of the, you know, the vision behind, you know, these programs at the beginning, and let's see, and then today we have actually for several years now, another major program with KACST, King Abdulaziz City for Science and Technology. So that one, you know, is a program between researchers and scientists, you know, from KACST and MIT. A lot of the topics are on water, energy, environment, labor, health, transportation. And they look at all of them from the modeling, simulation, monitoring, prediction, so that you can visualize and use these technologies for design. You can use them for planning, for, as I said, monitoring, prediction, at the city level, right? Or even at the whole country level, right? And then the other important thing is that not just to look at these domains, individual domains, let's say how the water is happening by itself, and then maybe the energy and so on, but then also how they are affecting each other. So that, for example, if you want to have like the metro in Riyadh, right? How would that affect, you know, other sectors? Okay, maybe the, I don't know, the water, the electricity, you know, these other things, and then you can see how, you know, these domains affect each other in terms of, as I said, you can collect the data and you process it. Very, very exciting research topics. Yeah.
You seem almost oddly perfect to ask this question, so I'll ask it. If you had the chance to design the city of the future, what is your vision? What is the city of the future 30, 50 years from now?
So I think maybe a lot of people would probably think about the buildings and maybe these things that. But from my point of view, I think the building things is the easy part, right? Because you have Either you have the money, and then if you don't have your own people to build it, you can bring other people to build it, right? Or you borrow the money, and then again, if you can't do it yourself, you can bring other people, and you can bring the top architects, the top urban planners, the top designers, and they can do that. But in that whole story, I think what needs to be done in the planning and the strategy and so on is the people. In many places, many cities, and sometimes maybe even countries, when the people are forgotten, then that city or that country doesn't go far. Doesn't go far in a sense where you can spend a lot of money, do a lot of efforts, but the return, is not at the level that you want. So one is the equation of the people there. How the people are going to live there, how they're going to prosper, how they're going to enjoy their life there, and how they're going to be very happy. So everything has to be around there. You build, the environment, in terms of what they call it, the public realm. You build everything that goes with it. That doesn't stand by itself. We have to add the economy that goes with it, right? And then the economy has to also match, what maybe a person is doing for 5 years or 7 years or 10 years, right? So that everything is in sync. It doesn't mean that has to stay there for 50 years or 100 years, right? Because things are changing. So we need to change and adapt, right? And then so the city has to be, a city or a region has to be dynamic, and it has to be, from, I think these maybe 3 points of view, is like the people, the environment, right? And then the economy that will sustain that. Because otherwise, if any one of these 3 is not done, properly, and also in concert with the others, right, then there will be an issue.
Right.
Yeah.
Fascinating. Do we have any questions from our audience? Would any of you like to ask a question? I think we have a microphone here. I'll ask another one while you guys think, because I know you're going to come up with something.
Sure.
So if these cities are sensing and adapting, how do we make the leap from adapting to changing, as you're saying, to keep people as the one of the focal points?
Yeah. So as I said, all of that has to go together. Okay. I've been involved in Singapore with a major collaboration between MIT and Singapore for, 17 years or so, and I learned a lot there. But Singapore may be a very good example. I mean, when they separated from Malaysia in like 62, 63, something like that, then you can see like almost like every decade, they moved like from one, for example, they started with like low skill manufacturing or production, and then they moved to higher level skill, and then maybe to the capital-based, economy, right, or the technologies capital, and then to the point where they reach, to the economy that is based on knowledge. And all of that one, did not happen like at once, but it was moving and adapting. And so for that, the people also have to adapt to that. Maybe you need new people. New people meaning in terms of their talent, in terms of their skills, in terms of their know-how, right? We cannot be like a standing still, right? So you go to school or for training, and then we stop. So if I stop, that means I'm going down, because everybody else is going up, right? So there is no like steady state of the stuff. So there's either going down or going up. So that's basically, so the people who are running, a city, a new city, an existing city, or a country, right? So perhaps with all of these tools now, it may be easier than before, because then you can see everything how it's working, right? You can even see what type of people you have, what is their education, what is their training, right? You can see, for example, where you might move, what kind of technologies or products or things that you would want to engage in, and how you do this matching. Because otherwise, I get into an area, but then I don't have the people or something else that can happen, and that mismatch can create a big problem. In fact, one of the cities in China that was built in 5 years. This is in Mongolia, like north of Beijing, maybe not too far from Beijing. 5 years, they built a whole city, with the buildings, beautiful, bridges and so on. But then something did not go well, according to plan, let's say, in terms of the business part. Okay, I think this is maybe the reason. So that place had everything, the buildings, the parks, the nice streets, everything is brand new. And this is a Chinese speed, 5 years they built a whole humongous, a mega city in that way. But then in the end, that other part of the economy didn't work out, and so now you have a ghost city, a city that nobody lives there, right? So I'm sure that they will find out a way how to, make a good use of that. But I'm saying that you can, one has to take these things into account.
That's right.
Yeah.
Well, living in just outside of Boston, of course,
Yeah.
the Big Dig then
Yeah.
is an interesting juxtaposition, right?
Yeah.
I don't recall how many years that took.
I think it started like in '93, around '93, and then it finished, 2005 or something.
Right.
So it was like...
So the
Yeah.
question becomes, a city built at China speed is
Yeah.
a city built from nothing to everything.
Yeah.
How do older cities adapt and start implementing these things?
Very good question. I mean, this way, another example, I think that people in the architecture domain and the urban planning and so on, they cite like different examples, and the one that comes to mind is the one in Spain, Bilbao. So that one, like in the 80s, it was like population was high, and employment was like maybe 25% or so, right? And it was basically a very depressed area. And so they decided, how to revive this whole thing. So then the idea came, to put a museum there, like the Guggenheim Museum, right? But in the end, it was not just the museum. There's the museum, and then everything that they did all around that, right? So there was a river that was polluted, contaminated, so they cleaned it all up. They built all the streets and the parks and the squares and whatever goes with that. They have about like an 8-kilometer waterfront for people to walk and jog and do whatever. And so they built all of this environment that goes with that museum, and then very quickly, it turned around and it became, a very attractive place, for people, not only to visit, but to live and work there. And now they have also a subway or transportation system. Yeah, it all worked out in that way.
So I guess we can never forget that it's humans that need to consume the experience of the city.
Yes, yeah. Otherwise, I think what it becomes is maybe like an airport. So people come to the airport to go somewhere else. So they stay there, somebody stay 1 hour, another person maybe a few hours, somebody spend the night, there's a hotel at the airport, they spend the night there, right? But the intention is not to stay there, to work there, to live there, to raise a family there, to maybe retire there. So you want people of this type, that they are invested, in this environment, so that they can do, I think, a lot more. And also from their, capability and knowledge and so on, they can give more. If somebody is just, there because for whatever reasons, but they are on, waiting for the next plane.
Right.
So their mind is not here. They might do the things that they need to do, but it's not perhaps with full capacity.
Right.
Yeah.
Fascinating. Well, Professor, thank you so much for speaking with us. We really appreciate it.
Well, thank you, Nick.
Yeah.
Thank you for having me.
And enjoy the rest of your time at
Yes,
KAUST.
I'm here today and tomorrow, and I go back to Boston tomorrow night.
Very good.
Inshallah.
Well, safe travels indeed.
Thank you so much.
Yeah, thank you.
Yeah.
And thank you to our online audience. Make sure to like, follow, and share the KAUST official channels on Twitter, Instagram, and LinkedIn. Tomorrow at 3 p.m., make sure and come back. We're going to be speaking with another MIT professor, Ahmed Ghanem. And that's all for now. Thank you.